Hi, my name is Justin Potts. I'm the head of engineering here at MoneyLion. MoneyLion is a fintech challenging the traditional banking system. Every day we ship software that creates a better financial path for our customers. We have a suite of financial products including banking, lending, investment, and credit building tools. Today the team is going to be giving a talk about Axon architecture, theory, and reality. In this talk we'll be analyzing architectural styles and characteristics we considered while building a brand new banking system. So we had a goal to upgrade our banking system. We had identified a new neobanking provider that would allow us to unlock some key functionality for our users. We had also identified some key limitations in our V1 banking system that we wanted to overcome. So with that in mind, we decided to rewrite our banking system from scratch with an eye towards the future. We had a lot of existing users that were going to be migrated onto this new platform and would be migrated fairly quickly. When releasing a bank, it's not enough to just release the ability to transact, for instance, credits and debits. There's a lot of things that have to be released coextensively or simultaneously. So for instance, integration with our other financial products was key. Regulatory compliance, integrations with analytics. There are a lot of things that go into a banking system to make it whole before it can actually be released to the general public. So this was a very big undertaking for both the team and the company, but one we were pretty excited about. This is our banking team. This pod is composed of 9 engineers, including the people speaking today. This is a very talented group of people who dealt with very difficult problem spaces, communicated well, and really gelled as a team to see this project to the finish line. We also had extensive support from our fellow engineers in Kuala Lumpur, Malaysia, in terms of helping with integrations and data analytics. Without the banking pod and support from Kuala Lumpur, this project would have not been possible. So a big thanks to everybody involved. So we had a couple of possible architectural styles to choose from. We knew that we wanted domain-based partitioning, we knew that we needed scale, and we knew that an event-based system would be helpful for operating or integrating with other services, as well as auditability. We came up with a list of 4 that you see here, mostly because they offered the things that we knew we wanted: domain-based partitioning, scale, and the ability to have an event-based system. So we came up with a list of architectural characteristics that we felt we needed. We grouped them into 3 categories, and we had a total of 11 characteristics. An architecture characteristic is something that meets 3 criteria. It specifies a non-domain design consideration, it influences some structural aspect of the design, and it's critical to the application's success. Many organizations call these non-functional requirements, but we feel like these types of things are really critical to the success of a project overall. An application could support a huge number of architecture characteristics, but definitely shouldn't. Since there's a trade-off imposed by every characteristic that you add to a list, the number of trade-offs grows as the number of characteristics grow. With too many characteristics, the design or the architecture style becomes confused between trade-offs and ultimately achieves none of them well. So we wanted to make sure to keep this list as small as possible, and we went through many iterations of this list before moving forward. So the first architectural style we looked at was the microkernel. The microkernel architecture is where the application logic is divided between independent plugin components and a core system. The benefits of this architecture are that it's quick to write and deploy, given that it's typically a monolith. It's low cost, given the simplicity. It can be domain partitioned, and it has good modularity via plugins. The pitfalls of the system are it has poor ability to scale certain components of the system. If any one of the particular code paths in the core system or a plugin component have more use than others or different architectural needs than the others, then it's likely to have to be decomposed. One of the other pitfalls is that we feel like core system bloat is likely. As the domain grows, as product requirements come in, or as the landscape shifts strategically, it's likely that your core system is going to have to take these things in, or they're going to have to go into plugins, meaning that either your core system grows or the number of plugins grows. Given that banking is a relatively complex domain, we felt like this was definitely likely to happen to us. We feel like it's really only suitable for smaller applications, although there are counterexamples to this in the world. A lot of tax prep software out there uses the microkernel architecture, but they have relatively low needs in terms of performance. The last pitfall that really dissuaded us from using this pattern was the lack of fault tolerance. It's not impossible to build in fault tolerance into a microkernel architecture, but it requires a lot of additional work and an additional infrastructure to make sure that it actually is fault tolerant. Next on our list was the services architecture. So services within this architectural style are typically coarse-grained portions of an application, usually called domain services. So you can imagine we have one service for lending, one service for banking, one service for wealth, so on and so forth. An important consideration for this architectural style is that it typically uses centrally shared databases per service, although that's not necessary. The benefits of this architectural style are that it's easy to deploy, it's easy for teams to swarm on, or build a shared understanding of. It encapsulates volatility, given that you have coarse-grained services, and typically if it's applied uniformly throughout your engineering stack, you are going to have less services, which means less network traffic between services, resulting in lower latency. The pitfalls of this services style architecture is the poor ability to scale components of the system. Again, we have the problem where certain code paths are going to have certain needs, and decomposition is likely. We also felt that database bloat was another likely possibility here, given that schemas would have to represent everything that the service handles or represents itself. Overall, we feel like this is a good architecture choice for many cases, given that the rule of thumb should always be to decompose when you need to. However, for us, building a V2 banking system, we knew already where our performance characteristics needed to be. We knew the critical code paths, and we knew that one service wasn't going to be able to meet our needs here. So the next architectural style we looked at was the microservices. And what I'm referring to here when I say microservices is a very naive implementation. So not a framework-based implementation like Eventuate Tram, not a highly DevOps-driven microservices architecture, but the one that companies typically start out with. So the benefits of the microservices pattern are the ability to scale individual components, good data isolation, assuming that every microservice talks to its own database, and having things split out in this way allows teams to parallelize work very nicely. Some of the drawbacks are what you would expect, things like latency. Large composition calls obviously take longer to complete. Chained calls, where you have a high number of microservices involved in the chain, also leads to a lot of latency. One of the other pitfalls is that your gateway layer, if you have a backend for front-end pattern or any kind of gateway pattern, needs to know a lot about your microservices. So you can expect multiple types of connaissance. So connaissance of execution, of timing, values, identity, are all going to be included in that kind of gateway layer. Another pitfall is that to do microservices well, in the non-naive fashion, you really need a chassis or a platform that automagically integrates logging, alerting, discovery, things of this nature into your microservices so that when teams spin them up, all of these things are kind of baked in. Until you have that, your microservices platform, usually every team is doing it in a full stack fashion. It's not very cohesive, it's not very uniform, and you'll find a lot of problems in this kind of situation. So a very mature DevOps culture is really necessary for heavy use of microservices. One of the other largest pitfalls is the ripple effects that are caused by typical microservices implementations. So if you haven't thought a lot about your decomposition strategy, if you've decomposed by function and you're only doing synchronous REST calls, then any kind of large product change or workflow change is going to have a ripple effect across many of your microservices. A typical example of this would be that if I am an investment platform and I allow people to trade stocks and bonds, but I want to allow them to trade cryptocurrencies. If I've decomposed my microservices functionally, it's very likely that the order, the bid, the execution system, all of these functional microservices are going to have to change to support this new cryptocurrency requirement. This is a thing you see a lot in microservices patterns because of the lack of really a solid decomposition strategy. Creating order really does require a lot of energy, and so this is something you have to think about up front. Lastly, when you're decomposing, it's usually better to do it when you have to, but microservices really entice people to decompose as soon as they can. So in closing, because banking is a very complex domain, going with a typical microservices architecture would require a lot of new automation, a solid decomposition strategy, bolting on event-driven logic, and really extreme efforts to avoid dynamic types of connaissance. Last on our list here was really Axon. We came across Axon a year ago. One of the reasons we initially didn't try to build out a CQRS system is because there's a lot of work involved in doing this yourself, building out event handlers, saga handlers, message routing layers, things like this. But after looking at Axon and looking at the friction points they'd removed, we renewed our interest in this kind of CQRS and maybe event sourcing pattern. Our team did a lot of initial scoping with Axon and the Axon framework to test pilot some of the features and found it really easy to get started with. So the benefits of this Axon microservices pattern are that it's highly scalable. It's very suitable for a system of record like a bank. We can split out read and write pathways at the very top, which offers very good segmentation as far as the architecture is concerned. It's heavily DDD driven, or at least DDD is heavily encouraged. That's something we wanted to keep. It allows for good volatility encapsulation via projections and events, and all of the things we didn't want to write were already written for us. The pitfalls of Axon kind of remain the same nonetheless. CQRS does have a learning curve, so if you have people that don't have familiarity with this architectural style, there will be an initial steep learning curve. And aggregate design is a very iterative and complex process. It can often take multiple iterations to really arrive at the correct set of invariants with the correct aggregate value objects and entities, things of this nature. So we did an assessment of the architectural styles mentioned earlier. One thing to call out here is that this assessment is really specific to our organization, and in particular to our engineering organization. If you have different levels of maturity with automation, DevOps, things like this, obviously you're going to weight these things differently. If you're aiming for different characteristics, this list doesn't even really apply to you, and you're going to make completely different decisions. But we wanted to really show you how we got to a good shared understanding of where we wanted to go and loosely how to get there. Now we want to segue into what we learned post-adoption about Axon's architectural fit, and to do that we'll go through how Axon measured up against each of the characteristics that we were aiming for. Handing it over to Tom.
Thanks, Justin. I'm Tom. I'm a staff engineer here at MoneyLion, and I've been here for about 5 years. And I'm going to walk you through some of these architectural characteristics and how Axon framework helped us sort of optimize them for our application. First one I'll go through is simplicity. So when I say simplicity, obviously everybody wants a simple system because they want to stay sane. For us, simplicity meant reducing the cognitive load between developers and like understanding how our whole application works without specialized knowledge like per component, right? We have a lot of other services in our company that all are implemented differently. And the goal with banking was to say, I could go, to one service and know how it works or another and have a common vocabulary between all of them. So needless to say, Axon was a great choice for helping us with this. Message routing, we use Axon Server Enterprise, and message routing is taken care of for you. That's typically a pain point in implementing a CQRS system is how do you get messages here and there, who's managing it, whatever. Also, the tools available obviously help you manage complexity. So as you're modeling your domain and modeling the application, you use that same vocabulary when you're designing as you do implementing. So a long-running process is a saga, or like, inspecting metadata on events is an interceptor. As you are developing it in theory, that translates one-to-one with sort of real-life implementation. And so when you understand how it works in theory, you more or less understand how it works in real life, which is pretty amazing. And obviously there are nuances, but that was a great joy. And the one difficult part with simplicity is event ontology. So when I say that, I mean like what is an event in your system? An event can be an instruction. It could just be a specialized piece of information based on something that happened in time, or it could be just the thing that happened in time. So an ATM withdrawal could be one event, or in another system it could be 5. It could describe that it was a withdrawal, and that it was a transaction, a user interaction. It depends on how you use them, but staying consistent with that and having consensus on what an event is and how they'll be used is super important, just to keep your design consistent and your design language consistent as it evolves. The next one I'll talk about is testability. So I don't think I need to go into why a system should be testable, but we can talk about how Axon helps with testing an eventually consistent system. So testability in any distributed system with events being passed around and different components talking to each other and listening is difficult. So it's like an airplane where if you say the fuel pump's been tested and the wheels have been tested, until you've flown the whole thing, I'm pretty sure you're not going to get on board. So it's the same way. You want to make sure you test it all in action. So Axon does provide test fixtures for sagas and aggregates and helps you model sort of how the state changes between an aggregate, or how a saga completes and progresses through its phases, and that's incredibly useful for keeping the complexity of your saga in check and knowing, this event will cause the saga to end, this next thing will proceed, it will meet this deadline, types of things that traditionally you would want the integration environment set up for. So you say, how do I enforce timing in testing, something like that, and well, check out the fixtures, they got it all. And as well with something like Axon Server and the way that consumers read events from the Axon event store, being able to sort of populate something like that and knowing consistently that it will read them and construct some state is really useful for just modeling different scenarios without a whole lot of boilerplate. And of course, integration and end-to-end is still difficult. Everyone might uses Axon a little differently, so you might not use Axon Server, you might use a MongoDB token store, and you might do state stored aggregates or event sourcing. I can't really envision one abstract but usable integration test suite that Axon could provide that would encompass all of these different setups. So a lot of it is sort of manual work to put up an Axon server in a Docker container and maybe do a Docker compose setup to have your components talk to each other. It's of course extremely worth it. It's not something you'll get out of the box, but everything that Axon does have will make setting it up fairly easy. So it's certainly something to invest in. Next up is deployability. So we can talk about the abstract benefits of the domain modeling and how you're going to test the whole thing, but eventually you want to put it on the internet, put it on a server or something. So we want to see, how do you deploy these things, and how hard is it, how easy is it? So a lot of positives here. Axon Server Enterprise is super smart with rerouting messages. So if you're using a container-based deployment system like Kubernetes, you don't have to worry about rolling deployments possibly missing messages or anything like that while the pods are transitioning. Because token claiming, is automated, and when a pod goes down, it releases its token claim, and when a new one comes up, it'll grab that. There's no sort of lost position, right? And so you're assured that they will pick up right where the previous deployment left off. As well, being able to scale on demand by adding new processors or new segments, splitting and merging, that sort of thing. Makes it really nice if you need to sort of scale down or scale up or anything while you're deploying. Likewise, if you have a more complex sort of deployment orchestration setup, you may have 3 different apps that have some chain of feeding events to each other. You're able to pause processors or scale them down, things like that, to sort of help coordinate that and make sure that you're not misfiring messages or that something's getting something it's not expecting. You can pause them at the start of the deployment and resume them when everything's up. You can really manage it a number of ways to make it super simple for you. So deployment hasn't really been much of a concern for us. And on that same note, with apps knowing what they're getting, event revisions with upcasting and lenient serialization can help with making sure that downstream apps or things talking to each other are getting the events that they expect. Lenient serialization is great because your events evolve and get more complex and more interesting. Those new fields won't trip up older systems, and you can always add some upcasters to derive new data or change their shape or whatnot. And and then other systems will have them just fine. So deployment, super nice. Don't think you have a lot to fear there. The last one under speed to market is interoperability. If you are like us and you have a lot of systems that are more synchronous and REST-based, and you're doing an eventually consistent system for the first time, you have to introduce it alongside those systems, and this is super important. So we had a lot of other services expecting REST interfaces. So you post to the payment endpoint, wait a few seconds, you get a response, and the payment is either done or it's not. So we had to ask ourselves, can these existing systems handle our eventual consistency, and how's that going to work, right? So what we resolved to do was have a pseudo-synchronous REST layer using subscription queries. So you say, post to the payment endpoint, we do that command that says do the payment, and then we subscribe to that status event and sort of block on that in the REST controller. And when we get a success or failure back, we send it back. This of course has caveats, right? Because you're not guaranteed to get that back in a certain amount of time, and so the system has to know how to interpret things like timeouts. Because if you're sharing the load on a system with really volatile or really frequent events, it might take a little longer to get that success. And so just be mindful of timing and what it means when something times out, because it's a little different than a synchronous service. So what we would say probably is you want to make sure you can adapt your eventually consistent system to a synchronous environment, but don't overfit it, because you're just obscuring the benefits of Axon and EC. And there are a number of solutions that you can provide to your team, like REST callbacks or their own projections and polling endpoints and things, so that they can embrace eventual consistency too, right? Because if your team's here, you're using Axon and doing some cool async stuff, they're probably pretty excited and want to adapt to it too. So really important to have good communication and set expectations correctly as you introduce a system like this. But there are a number of ways that you can make it work really well. So now we can move on to competitive advantage. So I don't think I need to tell Axon users here that Axon is very performant out of the box, and the CQRS system boasts a lot of performance gains over a normal web MVC or something like that. So I'll mostly talk about caveats here. But I will say that we have tens of millions of events in the Axon server event store right now. Hasn't caused any issues. There might as well be 50, 100, That's super impressive, and usually you would expect your event store to be one of the main targets for performance tuning and worries and not being able to sleep at night, but we're totally okay. So it's very impressive. Kudos for that. Things I will say, the configuration defaults for Axon Framework may hurt your performance. So there's a section in the documentation called performance tuning. If you're like me, you think, well, that's just for advanced situations or like high frequency trading or weird infrastructure choices. It's not. So definitely read it. It is all about tips and concepts for how to make your Axon framework setup perform well with your infrastructure and design. So things like batch sizes and token claiming and how that works with the type of database you choose for the token store. Those are all super important things to tune even at the outset, just so that you're not catching up with configuration as your system scales. And then the big thing for us, the big performance thing we noticed, was to take care with your tracking tokens. So keeping your tokens and projections in the same database is great, because then when you commit a unit of work, you know that you're progressing to the next event position, having done all of the work atomically that you expect it to. There's no deviation. But what ends up happening is you write and update those rows quite a bit as you're, processing these various events. And things like Postgres and other, typical databases have some weird caveats with updating rows a lot, especially rows with OIDs and reference tables behind the scenes and whatnot. And so if you keep it naive and use a batch size of 1 and do a replay of 40 million events, that's going to be a lot of updates, and Postgres is going to have to do a lot of vacuuming, and it's probably going to cause some issues. So again, make sure you're using the right batch sizes and token claim intervals, and just try to sort of deeply understand the magic behind the token store and that, because A, it's really interesting and impressive, and B, you're going to have to know it either way, but you might as well know it before it's 3 a.m. and you have to know it. So yeah, overall though, performance has been really incredible. These are just extra things to know. Next, I'm going to talk about evolution. And so when we say evolution in this context, it's all about making sure that the characteristics that we chose at the outset, like simplicity and testability and things, making sure those things stay fit as the system grows and changes and we add new features and new services and new expectations. So one great thing about Axon and what it can provide for you is parallelization, right? So if you divide your apps by context and by domain, while keeping like maybe a command and event registry as we've done, you can have people working on totally separate systems while sharing the same expectations about A, what sort of events are flowing through the system, but B, that you have a shared vocabulary and understanding of the concepts that you're using, right? So a saga in one service is more or less a saga in the other service, right? You want to handle events and set up a command model, you do that over here too. And so when you enter some new service, you know what to expect. And that's really been amazing for being able to jump on other projects and help somebody out, or being able to model new domains even though you might not know the business context, right? That's super powerful stuff, and we can just keep growing it. That's great. One thing that does change and has some difficulty is aggregate design. So anyone who's been doing DDD and designing out aggregates probably knows that they're going to change a couple times before you get them right, as your business requirements get distilled, and as you just understand your own context a little better. So Axon does provide a couple of sort of features that act as hints to what makes a good design in your system. So one is aggregate sequence number, basically saying the events that happen to an aggregate will be processed by handlers in order. So if I have 3 transactions, yesterday, today, and tomorrow, even if I parallelize all that work, my handlers are still going to process yesterday, then today, then tomorrow, which is great for enforcing like a running balance or just keeping a sane ledger, things like that. That can be one hint to make sure, where should I group these things? Should I use an aggregate or not? Well, that's a feature that you might want, and so maybe your aggregate can house those things together. And then one thing here is that Axon right now does not have built-in support for fitness functions. So I know that there are some libraries around like Arc4j and things that will sort of evaluate your system's modularity and stuff and does sort of static analysis there. That would be really amazing for Axon to provide as well. At the beginning when you do your design and you're sort of guessing a little bit, those hints are super important to help you along as you sort of get your design up and running. But I imagine down the line there will be even more support for doing that initial design. So that is all for me, and I will turn it over to Gaurav to talk about the remaining characteristics that we're looking for.
Thank you, Tom. So I'm Gaurav. I'm the lead engineer here on the banking team here at MoneyLion, and I would like to talk about scalability and how Axon helped us achieve scalability when it came to our application. So just a background, most of our application is read heavy. We have way more reads than writes to our application. I mean, we are a bank, and as you can imagine, people check their balance way more often than they perform a transaction or spend their credit card. Or I hope that's how things happen, and people are fiscally responsible. So what ends up happening when you are reading from a transaction from our application is you generally tend to read from a projection that can be created from our main application. And this is where Axon gives us the tools to create a new projection. So as long as this projection can scale itself, we are not worried about a spike in traffic when it comes to reads. There is, however, a caveat. The new projection is of course going to be eventually consistent, and as long as that is an established contract with your reading entity, this works well. Unfortunately, that wasn't as easy for us to achieve when it came to some of our legacy clients, which somehow relied on synchronicity when it came to our requests. They expected consistency, and while it was not immediate consistency that they expected us to have deadlines when it came to us catching up with the head of the token. And in certain situations, that did become a problem for us. There was some replication lag in some of our applications when we had not figured out all of our parameters for configuration. And monitoring the tokens was also a little more challenging for us initially when we were trying to onboard onto the system, and that did annoy some of our consuming applications. What did help us in this situation, however, was parallel processing. Anytime we realized that the replication lag was getting out of hand, we just simply added new event processors to the group, and we had more. We run on Kubernetes, so we just had to spin new pods, and the processors used to catch up. We would have, and essentially, one of the things that we did realize is you can't just keep adding new processors and getting rid of all the problems. Whenever you add more parallelization, of course, there's going to be synchronization problems. And in our case, it ended up hammering our token database, which was Postgres. So at one point, we added 1024 segments and realized how bad it ended up destroying our database, and we had problems. On the right side of things, we have the ability to add back pressure using Axon. At the end of the day, at some points, we just consider Axon to be a queuing mechanism in a way. And using that, we were able to add some back pressure and have scale when it comes to our writes. It wasn't the perfect way, but it definitely did help us in scaling well on the writes as well. Of course, it's difficult, as mentioned, it's significantly harder to scale on the write side than it is on the read side. We also had the ability, because we are using Kubernetes, we had the ability to scale some of the events that were more common than others, and thus our scaling was pretty independent of each other. The only thing that we wished we could have done was to use sagas more efficiently. Since sagas have only one processor and you have to rely on threads mainly to start scaling them, we were a little scared of using them. And on paper, sagas sound amazing. We just found it way harder to use sagas. We do use them in a couple of places, but not as much. Now we come to modularity, which goes hand in hand with scalability in a way, because we are able to split our processes into smaller modules. One obvious way is to have the command and query segregation, which, well, of course, is a common sense way of splitting your application. But because we are more service oriented and we have our application split in services as opposed to a tech-based partitioning, we are able to achieve scalability in a way that we hadn't thought of initially. Back in the day, when you had some old application framework, not old, but one of the tried and tested application frameworks, such as MVC, you could scale the front end, you could scale the back end, but you did not have the ability to scale certain parts of the applications. I couldn't just go and say, okay, let's scale the transactions side of things. Let's scale the part where users are checking balances. But because we are more service oriented as a result of Axon, as a result of projections, we are able to scale in different ways, and modularity that we have in our code base is important in that sense. We spent an incredible amount of time designing our aggregates, designing our domain model, and that is what had started paying off these dividends. And each of our domains, each of our aggregates lives on a new Kubernetes pod, a new instance. We could just add new pods in order to scale various parts of the application in an asymmetric way, which does give us new abilities. One of the advantages of doing that is because now they're physically separated and not just logically. We can track metrics as to how many calls are made from one aggregate to the other. Is it a problem for us? And as soon as we find out that there is more coupling between different aggregates, we can then split them and revisit our domain. However, we realized that redesigning aggregates was not a simple task. It wasn't something that an intern can do on the first day. And we had to spend some time in understanding Axon in order to perform that. And for some people, if you have upcasters in your event storage, they are going to live with you forever. And if it is a problem, well, that could be a negative for you. And finally, as I mentioned, we did get scared of sagas because of its scalability issues, or perceived scalability as far as our team goes, and we would have liked to use them more, quite frankly. So we were a little confused in situations where were we supposed to use sagas or aggregates. Next, we come to reliability. And we divide reliability into three parts: availability, observability, and durability. So as far as availability goes, we define it as a way whenever we have a consumer that wants to have a response from us. Availability is the metric that tracks how many times could we not respond to this consumer. Now, because we have projections that end consumers are reading from, we can have redundancy. We can have a primary master and slave database projection that the end consumer reads from, and both of them are populated based on events from Axon. Since this is an eventually consistent system, we can have as many of them as we want, and because of that, because of this redundancy, we can have failovers whenever there is an issue. And so it definitely helps in availability. We also, as far as observability goes, we can have auditing applications, and we have some of them. We call it monitoring applications that collect data points and do perform things such as user issue tracking, where instead of having one data point that gives us a story of what is going wrong, we can aggregate all of these metrics and have a higher level customer facing metric that tells us whether our application is healthy or unhealthy. And if our application goes down, observability is the metric that tells us how quickly we can respond to it. And because we have a system of record, it also gives us durability. The event storage, as long as the message made it to the event store, we can be sure that we can replay all of the events and make sure that every projection is recreated if something goes wrong. So because of that, we have low RPO, the recovery point objective. If something goes wrong, as I said, we just recreate, we go back in time, we play all the events, and then we have a new projection. The caveat though is event replaying can be a time consuming process. It's not something that is fun to do, and it's something that can hammer some of our resources. So the RTO can be time consuming. This is especially true if the batch size is not modified properly, and that was a lesson that we learned when it came to replaying events, especially when our event store started growing. And finally, one of the problems that we have is we have to make sure that the definition of availability does include eventual consistency. We have a lot of these synchronous processes that rely on our application, and if the consistency is delayed, we end up taking longer, and we use subscription queries for all of these synchronous applications. And if the consistency is not there, these subscription queries end up sticking around, occupying threads, and then it does affect our availability. And that's where our system started going down in availability. So that's again another reason why you have to move to an async architecture if you want to have availability. Audits are another part of banking. You are always going to face audits. Auditors are mainly interested in figuring out whenever something goes wrong, why it went wrong, what could have happened. And sometimes it hasn't even gone wrong, but you just have to show that the application was working as intended. And in the traditional architecture, what we had to do was we had to go back in time, look at logs, and figure out what might have happened and try to paint a story in front of auditors. Axon, because you have an event store, which basically is an audit trail for you, you don't have to paint any story, you don't have to figure out what's going on, you have it right there. All you have to do is replay all the events and expect your system to behave exactly the way it did the first time around. Of course, that comes with a caveat. You have to put processes in place which are making sure that the side effects that happen because of event replaying are not don't result in catastrophes. Like, you can't just move money twice just because you want to please an auditor. So idempotency of side effects is an important consideration that you have to put in place. And we had designed our application based on these principles right from the scratch. And it did pay us dividends a lot of times. We did realize that batch sizes are again an important consideration when it comes to auditability. And we had to make sure that all of our replaying happens with a good relevant batch size. The other important issue though is if an event is not in your event store and you're trying to audit that event, well, obviously you're out of luck. There is no way you can do that. And if someone tampered with this event somehow because of any exceptions, you're out of luck again. Finally, security. As we know, we're a banking organization. Security wasn't the first thing that came to our mind when it came to Axon, but we realize now how much we took it for granted. Axon definitely gives us role-based access when it comes to the Axon server, and that's something that does help us implement least privilege and need to know when it comes to our event storage. So that's definitely a pretty secure system right there. There are some indirect security considerations that we did not even think of, but now we realize the best way of working with data is not to have that data. And because we have a projection, we can decide, since the projection is based on end consumer, we can make sure that the sensitive data that the consumer doesn't need does not end up in that projection. So we don't have to use encryption to save data away from other malicious users. The other thing is crypto agility. If you want to change your encryption algorithm, it's pretty simple. All you have to do is create a new projection with this new encryption algorithm, reset your tokens, and replay all the events. And now your new projection will have all of the new data in the new, all of the existing data in the new encryption algorithm. So that crypto agility is definitely a plus. We also want to do a threat modeling lab which has a lot of our data, and that's something that's on my wish list, at least, where we want to run all of the events in a separate environment and start attacking them, performing penetration testing and chaos testing on all of these events to figure out how stable our application is, how resilient our application is. We haven't done that yet. I hope to do that soon, but again, it depends on product priorities. There are some benefits which are not because of Axon, but because we are on AWS. We have encryption in transit, obviously, because most of our stuff is on the VPC. We have TLS, and Axon does enforce some encryption when it comes to connecting to the Axon server. You can still connect without TLS, but it will annoy you by printing warnings. As far as encryption at rest goes, our event storage is on encrypted volumes, which is why we have encryption at rest. So you have to make sure that your event storage is not on encrypted volumes. And finally, because we are on AWS, we can isolate each network and make sure that if one network is under attack, the other projections are isolated from this attack. Of course, it comes at the design phase to make sure that your design make sure that each projection is in a network of its own. Now I'll hand it over back to Justin.
So in closing, there really is no objectively correct architecture choice. We could have gone with microservices, we could have gone with services, but for us, Axon really was the best fit for this situation. Axon eliminated a lot of the friction typically required for a CQRS and event store system. We did encounter some obstacles along the way that were not clear in the initial discovery process, but this is something that happens when you adopt any new framework. The banking domain is really complex. There's a lot of interactions. Having DDD and the ability to leverage Axon really did assist us with reducing a lot of that complexity and complication. Based on the Axon roadmap, we do expect friction to be reduced even further in the future. We don't really want to manage token databases. We do want to be able to parallelize the same instance of a Saga. There are other things we want as well, but we won't list them here. Ultimately, we had great support from the Axon team throughout this entire project. We had initial kickoff sessions. We had a Slack channel where we could hit them with any issue that we had. I guess one thing to leave the audience with is that early adoption is fun but stressful. Make sure that you really trust your team before moving to any new architectural style or framework, because it is going to be a steep learning curve for everyone involved. So you really need people that can pick things up fast and run with them. Also, as you'll see on the picture on the right, we had a Shiba in the office, which helped keep morale very high during recording a 3-man talk in a COVID world is a very complicated process, but yeah, thanks for bearing with us and we hope you enjoyed this talk.